Okay. Good afternoon, friends. Today we'll discuss normal linear spaces. Normed linear spaces. Audio వస్తుందా విజయ్? వస్తుంది కదా ఆడియో? ఓకే.
Sir, వస్తుంది sir.
Okay. Well, first we'll define what we mean by a linear space. Okay. Linear space. This is equivalently called a vector space. So vector space is a synonym for linear space. First, we will define what we mean by linear space. In fact, you should read these in your BSc also. We start with a non-empty set V. We start with a non-empty set V, right? And on this, we define an addition and a scalar multiplication. Okay, and to have a linear space, we should have a field also. F is a field. Okay. In this course, usually we take this to be R or C. This is of real numbers or this is of complex numbers. Okay. So first we define what we mean by a linear space. Let V be a non-empty set. Let V be a non-empty set. Okay. On this, we want an addition. So the definition of a linear space. First of all, we want V plus is an abelian group. Is an abelian group. Okay. What do we mean by this? First of all, it should be closed under addition. Okay. You take any two vectors from V. Let they be x and y, right? Then x plus y must be in V. Means addition must be closed in V cross V. Okay. We say addition is closed on V, right? This operation shows that plus is a binary operation on V. This condition says that plus is a binary operation on V. Okay, if you take any two elements from V, their addition is also in V. This need not be the usual addition. Okay, it depends on the case you take. Next, we want this addition to be associative. That is, x plus y plus z is equal to x plus y plus z for all x, y, and z belonging to V. Okay, and this means here first you are adding y and z, and then right you are adding y to z from left, and then to that sum you are adding x from left. Okay, but here you are adding y to x first from left, and then to that you are adding that sum to z from left. So the order in which you are adding is differing, but the ultimate sums must be equal. Okay, this should happen for every triple x, y, z coming from V. If this is the case, we say V is closed under associativity of addition. Okay, and then we want the third property, that is there should be an identity element. Okay, a 0 in V such that x plus 0 is equal to 0 plus x is equal to x for all x. Okay, for all x coming from V. This is if we have a 0, this satisfying this property, we say 0 is identity with respect to addition, right? And this is called additive property. This should be true for each and every x coming from V. And then let me move this menu. Yeah, right. That's safe. Okay. Now let's look at the fourth property. Right. Fourth one. Yeah. For every x in V, there should be a minus x in V such that such that x plus minus x is equal to minus x plus x is equal to 0. Okay, for every x in V, there should be a minus x in V such that the sum of x and minus x, whether you add minus x to x from right or from left, both these sums must be equal to 0. Okay, this should happen for each and every x in V. This property is called inverse property of addition. Okay, and then if the properties 1, 2, 3, 4 are satisfied, then we say V plus is a group under addition. Okay, in addition to these 4 conditions, if we also have that x plus y is equal to y plus x for all x and y coming from V, we say V plus is an abelian group. We say this is the commutative property of addition. Okay, x plus y, y plus x. X is added to y from left. Here it is added to y from right. Okay, the order of addition is different. Okay, even if it is so, if the final sum, ultimate sums are equal, then we say, and if this is true for each and every pair of x and y coming from V, sometimes x can be equal to V also. Okay, for each and every pair of x and y coming from V, whether they are equal or not, whether x and y are equal or not, if x plus y is y plus x, we say V plus has a commutativity also. The properties 1 to 4, that is group properties plus commutativity, make V plus an abelian group. Okay, after this we want a scalar multiplication on V like this. In fact, what is happening is this plus is a mapping from V cross V into V, because it is closed. This x and y are coming from the Cartesian product V cross V. Okay, and because the sum is again in V, so the plus image of an ordered pair coming from x and y coming from V cross V, that is x comma y, is taken to x plus y by this plus. Okay, so plus is a binary operation by the property 1. Plus is a binary operation on V cross V. We say plus is a binary operation on V, and also we say V is closed under plus. Okay, and then we want a dot to be scalar multiplication on V. Okay, we define it as follows. Right. So yeah, we want dot to be right. We want scalar multiplication dot to be a function from f cross V into V. Okay, what kind of elements are there in f cross V? You have alpha comma x or c comma x. Okay, you have c comma x coming belonging to f cross V. C is a scalar and x is a vector. Elements in V are called vectors in generally. But even if they are numbers or matrices or functions, in generally we call elements in V are vectors. Okay, so the c comma x is a member in f cross V, and this is taken to c dot x. Okay, the c has to be small. It is c dot x. Okay, and this is also written c into x. We suppress x, by that we mean c dot x. Okay, so dot is scalar multiplication f cross V into V. If this is true for each and every c in f and x in V, we say scalar multiplication is closed on V. Okay, see, f is field. Usually in this course we take f to be the set of real numbers or the set of complex numbers. Okay, right. Well, we want the sixth property for scalar multiplication. We want c into x plus y is equal to cx plus cy. Okay, means here we are suppressing dot. It is c dot x plus y is equal to c dot x plus c dot y for all x and y coming from V and C coming from F. Okay. So X and Y are coming from V. So X plus Y is an element in V. So this is an element in V and this is an element in C. So this C comma X plus Y is an element in this Cartesian product. Okay. And so we can speak of this Cartesian product C dot X, this scalar product C dot X. Okay. This is also a scalar product. This is a scalar, this is a vector. Okay. Elements in field are called scalars. So scalar times vector is a scalar product. This scalar, this is scalar, this is vector, this is scalar product. Okay. Because of this property, let us call this property 7, 6, and this is 7. Okay. No. So by the property 6, scalar product is closed on V. Therefore, there is an element in V. C to X is an element in V. C into Y is an element in V. In V, we can add any two vectors. So this is vector addition. Okay. This also means that this scalar multiplication is distributive or addition. Okay. C into X plus C into V. It is called the distributivity of scalar multiplication or vector addition. Okay, this should be true for each and every X and Y coming from V and each scalar C coming from the scalar field. Right. Similarly, we want scalar multiplication to be satisfying these values. C1 dot C2 dot X must be equal to C1 dot X plus C2 dot X. Right. Here C1, C2 are scalars, or any scalars coming from F. Okay. This addition is the addition in the field because C1, C2 are scalars. So this is the field. This is the addition in the field. Okay. So this is scalar addition, and this is scalar product. So this is a scalar. Scalar times a vector is a scalar product, and this scalar product is assumed to be closed. Right. If we assume it is to be closed, then this scalar product is in V. Therefore, this is a vector in V. Similarly, C1 is a scalar, X is a vector, C1 dot X is a scalar product, is an element in V. If we assume V to be closed under scalar multiplication. Similarly, if by the property 6, this is a vector in V. So this is vector addition. This is vector addition. This is scalar addition. Okay. This speaks about the distributivity of scalar multiplication for scalar addition. Okay. Right. Then we have a couple of multiplication products, couple of multiplication properties. Okay, let's see. Yeah. Right. This is 9. Yeah. We want C1 C2 into X is equal to C1 into C2 X is equal to So let me see. Right. Okay. So here C1 C2 are scalars is a vector. So this is C1 C2 dot X is equal to C1 into C2 dot X. Okay. This same is. Okay. So this is C1 C2 are scalar. This is scalar. This is multiplication in scalar. In between these two, you have the multiplication in the field F. Okay. This is the product of scalars. And here you have the scalar multiplication. This is a scalar. This is a vector. So this is scalar multiplication. Okay. We haven't written. Okay. So this is scalar. This is a vector. In between them, we have scalar multiplication. And this is the right. This is defined between defined on F cross V. Okay, and this is a scalar product. So and this is a vector. We assume because of this is a vector. We are multiplying this vector by another scalar. So in between them we have scalar product, scalar multiplication. Okay, then A scalar is multiplying a vector, so this again is a vector in V because of this. Okay, so if this also is true, means the order in which you are multiplying x by these scalars is immaterial. Okay, ultimate products are same. Okay, this is a kind of associativity. Okay, the final one is this: we want 1 into x is equal to x for all x coming from V. Okay, for all vectors x, we should have 1 dot x. This is scalar multiplication. If you multiply x by, this is the multiplied by int in the scalar field. If you multiply vector x in V by multiplied by int 1 in F, and you should get x, right? You should retain the identity of x. Okay, so if a non-empty set V with plus and dot satisfies all these properties 1, 2, 3 up to 10, we say this is a linear space. Okay, and we also say it is a vector space. Equivalent, these two are equivalent and synonyms. Okay, and we or the field F. Okay, let's look at some examples. Yeah, examples of vector spaces. Okay, the first one, this is the very simple one. We have the set of real numbers. Right? And field is this of real numbers. So so we are equipping R with the usual addition on real numbers, and usual multiplication, scalar multiplication is the usual multiplication on real numbers for the field R. Okay, this is a vector. This is a linear space. Okay. Okay, we know how to add two real numbers. If x and y are real numbers, we know how to add them. If we add two real numbers, we get back two real numbers. We get back a real number. So plus is closed under R. Okay, and then addition of real numbers is associated. Okay, and this is true for any triple xyz coming from R. Okay, you have associativity of addition on R, and then you have if you add the 0 number to x, either from right or from left, the final sum is x. It retains the identity of x. Okay, the addition of 0 from either side retains the identity of x. This is the identity property of x. Okay, and then you have x added to minus x. For any real number x, you can add minus x. Okay, if it is plus 10, you can add minus 10. If it is minus 20, you can add 20. So x from either side you can do it. Okay, this is equal to 0. The sum is equal to 0. Therefore, so every real number has additive identity. Okay, this is the inverse property. Every real number has inverse element, and this is inverse property. Okay, and then so these four conditions give you that. These four conditions will give you that R plus is a group. Okay, and we also know that x plus y is equal to y plus x. Okay, for all real numbers x and y coming from R. This is commutativity of addition. Okay, the order in which you add is unimportant. Whether you add from right or from left, the ultimate sums are same. So this is an abelian group. Okay, and then we have the multiplication, scalar multiplication. You can add a real number. By another real number. C is a real number. Your F is R. Your field is R. So C is coming from R, coming from F, that is R. So your C is a real number. Your X is coming from V. V is equal to R. X is a real number. This is the usual multiplication. You define the scalar multiplication to be the usual multiplication of real numbers. Then your scalar multiplication is a mapping from F cross V into V. It takes R cross R into R. Okay, into R. Right. This second erase. Okay. And then we have the remaining 5 properties also. You have c into x plus y is equal to cx plus cy. Okay, if if c, x and y are real numbers, okay, if x and y come from here, here in this case v equal to f equal to r. So c, x and y are coming from r, you can show this. Multiplication is distributed over addition. Okay, and also you have this. Also you have c1 plus c2 into x is equal to c1x plus c2x. For any three real numbers c1, c2, x, you can show that c1 plus c2 into x is c1 into x plus c2 into x. Okay, this is a kind of expansion of multiplication over addition. Okay, this is the distribution of multiplication over addition from right. Okay, and then we also know that these are here c1, c2, and x can be any real numbers. And we also know that c1 into c2 x is equal to c1, c2 into x for all real numbers c1, c2, x. Okay, and also we know that 1 into x is x. Right? This is the usual multiplication. In this case, our scalar multiplication is the usual multiplication. Okay, 1 into x. If you multiply 1 and x for any real number x, we get back x. Okay, so these are the usual multiplication and the usual addition show that r plus dot is a vector space for the set of real numbers. Okay, so this can be called example 1. Let's look at another example. This is a kind of non-example. This is a kind of non-example. I want to take r plus dot and then over c. Okay, my v is r and f is c. This is a set of complex numbers. Okay, yeah. I want to take v as a set of real numbers. So I want to check whether this is with respect to the usual addition and usual multiplication, whether this is a vector space or linear space. Okay, I want to add any two real numbers. You can easily see that with the usual addition of real numbers, with the usual addition between two real numbers, r plus is an abelian group. Okay, as in the previous example, you can see that r plus is an abelian group. And now I want to define scalar multiplication. Okay, from c cross r into r. Yeah, is this possible? Yeah. So I want to multiply a complex number a plus ib, right? And then right. A plus ib, comma. Here I will take a real number c, right? C is coming from R, a plus ib is coming from C. A and B are real numbers. So a plus ib is a complex number. So I want to define this into R if possible. Okay, I want to do this multiplication. I want to multiply a plus ib from left with C. Okay, I want to multiply C by a plus ib from left. So I want to define this as, right, this is the usual multiplication of a complex number and a real number. This can be treated as usual multiplication of complex numbers. So it is what is this? A into C plus I into BC. Okay, I into BC. So this scalar product is defined like this. Now if you take B and C such that BC is not equal to 0, then you will have a non-zero imaginary part. Therefore, and in that case, this scalar product is not present in R. Okay, so for example, if you take if you multiply I2 by 3, right? I will take 2 to be B and A to be 0, C to be 3. Then this is mapped to I2 into 3, that is I6. Okay, this is not a real number. This is purely imaginary. Therefore, Therefore, under the usual multiplication of complex numbers and the usual multiplication addition of real numbers, this is not a linear space. This is not a linear space. Okay, here I must delete not, otherwise not becomes S. Okay, so yeah, this is an example, this is a non-example, this is not a vector space. Okay. And then yeah, I want to speak about norm, right? Norm also means a rule, right? Literally. Okay, norm, right? Yeah, mathematically we treat norm as a function. Okay, if we have a function, say we have a vector space V plus dot or a field R. Okay, say we have a vector space or a linear space V or a field, and on that we will like to define a function, a special function called norm. Okay, this is this we want to define as a function from V to V to V, yeah, from V to V, right? It takes an x here to norm x. Okay, and it should be satisfying these conditions. One, norm x, yeah, here we should have not, it is not V, it is R non-negative. So we must have here the codomain must be not R or non-negative, this set of non-negative real numbers. Okay. So we want to define a particular function from V into the set of non-negative real numbers satisfying these conditions. Number one, norm x is equal to 0 if and only if x is equal to 0, and two, norm alpha times x or norm c times x. Okay, yeah, is equal to mod alpha norm x. Okay, for all alpha coming from field and x coming from the vector space. Okay, this is called scalar multiplication property. Okay, norm of a scalar product is modulus of that scalar times norm of that vector. Okay, this should be true for each alpha coming from the field and x coming from the vector space. Okay, and finally we want the triangle inequality. Norm x plus y must be less than or equal to norm x plus norm y. Okay, here x and y are any vectors. Okay, so yeah, for example, if we consider R2, right? If we consider R2, this x are coming from R2. If your V is R2, R2 can be seen to be a vector space over R, the field of real numbers. Okay, here you can add, yeah, here you take any 2 points, right? Or you take any 3 points. You take 3 points. Okay, you join them with line segments. Okay, this is one, right? And we can show the right here. You can name these points P, Q, S. Okay, PQ can be taken to be the vector x, QS can be taken to be the vector y, and PS can be taken to be the vector z. So norm x can be norm can be taken as the length of sides, length of distance between 2 points. Norm can be the Euclidean distance between 2 points. Okay, so in that case, norm of z will be length of this vector, this side. Norm of y will be the length of this side. We know in any triangle, length of one side is less than or equal to sum of the lengths of the other 2 sides. That's how you will have this. Okay. That's how if you take x to be this, y to be this, this may be x plus y, right? This may be x plus y z. If this is x and this is y, this may be x plus y. Okay. In fact, yeah. Let me show it exactly. So, okay, and then you take two vectors. This is x and this is y, right? This can be called x, this can be called y, and you form a parallelogram with these two as the laterals and the adjacent sides. Okay, how you draw a line parallel to this? You draw a line parallel to this, right? And you draw a line parallel to this. This is parallel to this. This is parallel to this. So this is a parallelogram. Okay, and if you join this vertex with the origin, then what you get is a diagonal. Is a diagonal of this parallelogram, right? So this is x, this is y, this is x plus y. Okay, so the vectors x plus y, x and y form the sides of a triangle, and in a triangle they have to satisfy the triangle inequality. Length of one side is this, length of this diagonal is this, length of the sum of the lengths of the other two sides is this. Okay, that's how this is called triangle inequality. Triangle inequality. Okay, so on a vector space, we can define a function norm with these three properties. We can define a special function satisfying these three properties. We say that this function is a norm on this vector space, and in fact we call V dot is a normed linear space. Is a normed linear space. Okay, because on a vector on a linear space we are defining a norm. So this is called a normed linear space or a normed vector space. Okay, let us give some examples for vector spaces. Example 1. Okay, let me call this example 3. Continuing with the examples on linear space. Okay, yeah. You take V to be the set of real numbers. Okay, and the usual addition and usual multiplication, or the scalar multiplication. Usual addition is the vector addition for the field of real numbers. This is a vector space. Okay, on this vector space you can define norm of any real number to be its modulus value. Okay, the absolute value function. Then you can show that this right. If I define this, then you can show that this definition satisfies all the conditions of a norm. Okay, this is non-negative. Norm of x is the modulus function is mod x. Mod x is always non-negative for all real numbers x. Okay, let me see how many participants are there. 6 are there. Okay, do all of you belong to first year or second year? Hello, friends.
Second year.
Second year. Hello.
Second year, sir.
From which place?
Mahbub Nagar.
Oh, I see. Anybody is from Twin Cities? Anybody is from Hyderabad? Okay. Okay.
Sir, one request.
Okay. Okay. No problem.
Sir, one request, sir.
Are you able to follow this? What I'm saying? What I'm teaching?
Sir,
are you able to follow?
Sir, one request. Your voice is, your pronunciation is somewhat faster. So your words are not that much clear, audible.
Ayo. Okay.
Just pronunciation, just make it slow, sir.
Oh, I see. Okay.
Thank you, sir.
Norm x, yeah. Let us take the absolute value function. Okay. Absolute value is always non-negative. Therefore, right? Well, how do you define absolute value function? It is x if x is non-negative, and if it is minus x if x is negative. Okay. If x is negative, minus x is positive. Otherwise, right? If x is greater than or equal to 0, it is x. So in any case, it is greater than or equal to 0. So modulus value function is always non-negative. So norm is non-negative. here also we have norm of x is equal to 0. Let us look at this. Means mod x is 0. Okay. Mod x is 0 means x has to be 0. There's no other goal, right? Otherwise, if x is non-zero, if x can be negative, then minus x will be positive. If x is positive, if x is non-zero and if x is positive, then x is positive. So in any case, if in case your x is positive, right, means there is non-zero. So x has to be non-zero. So this is equivalent. X equal to 0 plus mod 0 is 0. And this implies this, because x not equal to 0 means this has to be positive. This has to be not equal to 0. Okay, so therefore it is if and only if. So this we do have. And the second one is norm c times x is mod x is modulus of cx. It is modulus of cx. Modulus of c times x, right? It is mod c, no, it is, yeah, it is mod c mod x. Okay, right? Mod, I must erase this. Mod, I must erase. Okay. So norm cx is mod cx. This is mod c times modulus of product is product of moduli. Okay. So now this mod x again can be written as norm x. So that's how the second condition, the definition of norm is satisfied. Norm of cx is mod c times norm x. Okay. The third one is norm of x plus y. Here c and x are real numbers. Okay. And norm of x plus y is equal to mod x plus y. Modulus satisfies the triangle inequality. Is less than or equal to mod x plus mod y. Okay. So this can be written as mod x can be written as norm x plus mod y can be written as norm y. This is true for any real numbers x and y. That's how the absolute value function becomes a norm. Okay. And or equipped with this norm is a normal linear space. Okay. Or with modulus value function is a normed linear space. This is called the usual normal linear space. This is called the usual normal linear space. Is a normal linear space with the usual norm. The usual norm is the modulus norm. That is the Euclidean distance norm. Okay. What is mod x? What is mod x? If x is here, this is origin. It is the distance of x from origin. It is this much. Okay, from 0 to x. If your x is on this side, right? If x is positive, it is here. If x is negative, it is here. So the distance between these two, 0, x and origin is this much. Okay. So mod x is the distance of x from the origin. So this is the Euclidean distance function. Okay. That is example 3. The next one is this. Example 4. Right. Yeah, you can take the Euclidean space Rn or cross or taken n times. Okay, this is the Euclidean space, right? And yeah, on this is our V. This is our V. Okay, we have to define an addition and a scalar multiplication. Okay. Of course, the field is R. We take F to be R, right? So here we have to take n, right? This is Cartesian product of n sets. So so we have elements of the form x1, x2 up to xn, right? Elements in this Cartesian product of n sets is formed of n tuples x1, x2 up to xn, where each xi is coming from R. Okay, this belongs to Rn, right? So to add two vectors in Rn, we should take another vector also. Let us take it to be y1, y2 up to yn. Okay, let us take this also to be from Rn. We want to add these two vectors. This may be defined to be x bar. This is not conjugate of x. Just a symbol. I am denoting this n tuple by x bar. I am denoting this n tuple by y bar. Okay, this is only a symbol. So I want to add x bar and y bar. Okay. So I want, okay, I have x1, x2 up to xn, and then I want to add these to y1, y2 up to yn. Okay. This is an n tuple, this is an n tuple. I will define to be, I want the sum also to be an n tuple. So what I do is I'll add the corresponding elements. I'll add the first coordinates x1 and y1. Right? I add the second coordinates x2 and y2 and write it as the second coordinate of this new n tuple. I'll add the first x coordinates and write the sum as the first coordinate. I add the second coordinates x2, y2 and write it as second coordinate, and so on. I'll add the nth coordinates. I will add the nth coordinates and write the sum as the nth coordinate. This is called coordinate-wise addition or component-wise addition. Okay. So if you add like this, you get again an n tuple again. You can, right? Your xi's and y's are real numbers. So each of these is a real number. Okay. So this sum will also be an n tuple of laying in Rn. Okay. That's how on Rn we can you can define an addition. Okay. And here which is closed. This, if you define like this will be closed, right? Because this is present in Rn. Okay. So and then you can also see that because addition of real numbers is associative, you can show that x bar plus y bar plus z bar is equal to x bar plus y bar plus z bar. Okay. If you take in the third vector z bar equal to z1, z2 up to zn lying in Rn, you can show that x bar plus y bar plus z bar is equal to x bar plus y bar plus z bar for any x bar, y bar, z bar coming from Rn. Okay. This speaks about the associativity of vector addition. Okay. This you can show. This is because of real numbers, because in R addition of real numbers is associated. Okay. That's why you have this. Okay. And then you have what is zero vector for addition? What is zero vector? It is x bar plus 0 bar equal to 0 bar plus x bar is equal to x bar. What is this 0 bar? It is 0, 0 taken n times. Zeros. This is an n tuple formed of zeros alone taken n times. Okay. This is an element in Rn. This works out to be additive identity. Okay. You take y1 equal to 0, y2 equal to 0 up to yn equal to 0. x1 plus 0 is x1, x2 plus 0 is x2, and so on. xn plus 0 is xn. So x bar plus 0 bar will be x bar. Okay. And if you take xi's to be 0 and yi's to be coordinates of x bar, you can show 0 bar plus x bar is also x bar. So that's how you have this. This is additive identity. You can also define x bar plus minus x bar is equal to minus x bar plus x bar equal to 0 bar. Okay. If you are given a vector x bar to be this, okay, you have to define minus x bar. How can you define minus of x bar? This you can define as, this is x bar. Okay. You take negatives for each coordinate. So you have minus x1, minus x2 up to minus xn. Okay. This works out to be, this is the definition of minus x bar. This is the additive identity of x bar. If you define like this, for x bar equal to this, you can show that x bar plus minus x bar equal to 0 bar. Similarly, you can also show that this is also 0 bar. Okay. So the properties of plus up to this make this addition a group, and you can as well show that x bar plus y bar equal to y bar plus x bar. Okay. Right, because x1 plus y1 can be written as y1 plus x1. x2 plus y2 can be written as y2 plus x2, and so on. And xn plus yn can be written as yn plus xn. So that's how this can be split. This can be split as y1 up to yn plus x1 up to xn. Okay, because of the definition of this, right? This sum is sum of these two. Okay, so x1 plus y1 can be written as x1 plus y1. Okay, this y1 plus x1 can be written as this x first coordinate plus this first coordinate x1, and y2 plus x2, y2 comes here and x2 comes here. Okay, that's how yn plus xn, right, is yn comes here and xn comes here, and this is and right. So this is equal to this, this is equal to this, and again this is y bar, this is x bar, this is equal to y bar plus x bar. That's how you have x bar plus y bar is y bar plus x bar. Means this point-wise addition or coordinate-wise addition is commutative. That's how V plus is an abelian group. Okay, and then we have to speak about the scalar multiplication. Right? We take a real number a and we want to multiply it by x1, x2 up to xn. Okay, this is a vector. Scalar times a vector x. This is x or x bar. Okay, this n tuple can be called x bar. So we want to multiply a vector by a scalar. For me, a is a real number. Okay, let a be a real number. So we want to multiply this n tuple by a real number. How? This way. We'll multiply each of these by a. We multiply each coordinate by a. What do we get? A into x1 plus a into x2 up to a into xn. Okay. See, n tuples can be thought of matrices. How do you multiply a matrix by a scalar, by a number? We'll be multiplying each of the elements of the matrix by that number. That's what we are doing. You multiply each of the coordinates by that number a into x1, a into x2 up to a into xn. Okay. This is called component-wise or coordinate-wise multiplication. That's how we define this scalar product to be this one. Okay, and xi's are real numbers. So this is the product of two real numbers is a real number. Product of these two real numbers is a real number. Product of these two real numbers is a real number. All these are real numbers. Therefore, this is present in Rn. So your scalar multiplication is closed on Rn equal to V. Okay, and then you can see that all the remaining properties of a vector space are also satisfied. In fact, you have this. You have a into x bar plus y bar. X bar plus y bar is equal to a x bar plus a y bar, and then a plus b into x bar is equal to a x bar plus b x bar. Okay, for me b is a real number. A plus b times x bar is a into x bar plus b into x bar, and then you have a b into x bar is equal to a into b x bar, and then you have 1 into x bar is equal to 1 into x bar. How do we define this? This is defined as 1 into x1 up to xn, right? It is defined as equal to, right, 1 into x1 comma 1 into x2 up to 1 into xn. By the definition of the scalar product, multiply this scalar product as 1 into this, and then 1 into xn up to 1 into xn. Okay, this is what 1 into xn, x1 is x1, 1 into x2 is x2, and so on. 1 into xn is xn. It's nothing but is x bar. Okay, so this is the final property of in the definition of a normal linear space. Okay, that's how your Rn under the point-wise addition and the this is component-wise addition or coordinate-wise addition, and this is the coordinate-wise multiplication. This is a vector space overall. Yes. Any questions? Okay. Okay. Now, right. Now, let me talk about. A okay. Now, let me talk about this one, the Holder's inequality. Let me talk about the Holder's inequality. Holder's inequality. Okay. It says the following: sigma mod xi yi, where I equal to 1 to n is less than or equal to sigma mod xi of p, where I equal to 1 to n whole power 1 by p into sigma mod yi or p, where equal to 1 to, no, here comes q. Yeah, whole power q whole power 1 by q. Okay, where I equal to 1 to n. Okay, here p and q satisfy this. 1 by p plus 1 by q is equal to 1. Okay, p and q are real numbers. P and q are real numbers, and your xi and yi are also real numbers. For all I equal to 1 to n. Okay, for all I equal to 1 to n. See, this is an inequality. This is an inequality. This helps in proving the properties of norms on certain vector spaces. Okay, this is an inequality. Right? This helps us to prove certain inequalities in the definition of norm on certain vector spaces. Okay, here x and y are multiplied, the product of real numbers, and you're adding those products. Okay, this product can be split into product of these two real numbers. Right? Xi's are real numbers, so xi power p is a real number, p and q are real numbers. So this is a real number. This is a sum of n real numbers. Okay, and its pth root is taken. And then this again, y is a real number, so mod yi is a real number. Qth power is a real number, so this sum of n real numbers, its qth power is taken. So this this inequality is called Holler's inequality. Now let me take a PDF file, and there are some mistakes, a couple of mistakes. Let me show them to you. Yeah, how can I have this one? Share, I think. Yeah, it is share. Okay, share, and then I want PDF. Where can I have PDF? Okay, let me open for 1 minute. I'll open that and then come. Let me open a PDF file. What is here? It is in norm. Which one I want? Yeah, I want Holler's inequality. It is in page. Yeah, this one. There are two printing mistakes in Holler's inequality. Yeah, I want to correct them. Right. Yeah. Please look at this. Here it should be dot multiplication. Okay. Can I write on this? Here it should be dot. No. Yeah. Can I write on this? No. Oh. Okay. Normal linear spaces. One minute. Let me write down this normal linear space. Okay. Is it this? Which one I want? Holler's inequality I want. Yeah, maybe this. Okay, you please open. You please open. Hello, is anybody there? Hello.
Yes, sir.
Please open page 10. You please open page 8. Please open page 8. Not this. Page 8. Page 8, line 5 from bottom. Page 8, line 5 from bottom. Could you see? Hello. Four. Is it this or this? It is this. Which one? Is it this? No. Is it this? No, it's not even this. Let me try. Yeah. In this page, let me magnify. Hello. You look at this. You look at this. This one. This one. At this point, this should be dot. Okay. In page 8, fifth line from bottom. Hello, students. You please correct this. This should be dot. A power 1 by q dot b power 1 by q. A power 1 by q p dot b power 1 by q. Okay, this should be dot. And again here in the next page there is a mistake. In 1, 2, 3, 4, 5, 6, 7th line. It is this. Yeah, it is this. Here. Right here. Here it should be less than or equal to. Here this inequality should be less than or equal to. Okay. And in this, what we are doing is we'll show that this function. Let me magnify. No. Right. Yeah. Here we define a function 1 by q plus t by p minus t power 1 by p. We make use of this. Okay. We define a function 1 by q plus t by p minus t power 1 by p. We consider this function. We call this x of t. Okay. For this function, we calculate x dash t. What is x dash t? It's a constant, so it is 1 by p. It is a t term. This is 1 by p minus derivative of this is 1 by p into t power 1 by p minus 1. Okay. We are taking 1 by p plus 1 by q is 1. So this will be minus t power 1 by q. So you make yeah. So let us see. Right. So what we are doing? Are you able to see what I'm writing? Must be able to see. It is screen share. Okay. Right. So yeah. Now what you consider this for t greater than or equal to 1. You consider this for t greater than or equal to 1. So this thing t power 1 power anything is greater than or equal to 0. So this thing is greater than or equal to 0. Minus of this is less than or equal to 0. Okay. How about this 1 by p? Right. Yeah. He says to take out 1 by p. This is 1 by p into what? 1 minus t power 1 by q. What is 1 by p plus 1 by q? It is 1. So 1 by p minus 1 will be minus 1 by q. Okay. Now, if you consider this for t greater than or equal to 1, what happens? Yeah. It is you consider t power minus 1 by q. T power, why it's not writing? It is t power hello. Okay. No, it's not writing. I don't know why. Okay. I don't know why it's stuck. Okay, we'll show this x dash t is negative. Okay, for t less than 1 and positive for t greater than 1. Means we'll show that this on the left hand side of t, on the left hand side of t equal to 1, x is decreasing, and on the right hand side of t x is increasing. Therefore, at a t equal to 1, x will be taking local minimum. Okay, so we'll that's how we get x of t is greater than or equal to x of 1, and using that we'll obtain the Holder's inequality. That is the basic idea. We'll show that x of t is greater than or equal to x of 1 in a neighborhood of 1. we are proving that the Holder's inequality. Okay. What were we doing? We are proving Holder's inequality. We have taken this function. This should be dot, right? And we bring in this function 1 by q plus t by p minus t power 1 by p. Will show that this has a minimum at t equal to 1. By finding its derivative, we'll show on the left of 1 it is decrease, the derivative is negative. On the right of 1 the derivative is positive. Therefore on one side it is decreasing, on the other side it is increasing. So at t equal to 1 this will attain a local minimum. Okay, right, or minimum. Okay, so we'll get x of t is greater than x of 1. That gives, right, that gives this inequality, right? So that gives this inequality. In this inequality, okay, by taking a by b, t equal to a by b, we can obtain this inequality. Okay, we can obtain this inequality, right? We because of x of t greater than x of 1, we obtain this inequality. In this inequality, we take t equal to a by b, then we can obtain this inequality. So right, with dot here, not plus. Okay, and then we take a to be ai to be this one mod x power mod xi power p by sigma mod xy power p, and bj to be mod y power q by sigma mod y power q. Okay, these are your ajs and bjs. We apply this to aj into bj. Okay, by this inequality. This is this into this. Okay, we will apply for aj power 1 by p into bj power 1 by q is less than or equal to aj by p plus bj by q. So that, and then we add up, we add up all these. Okay, and we apply this equality, and that gives this in this whole thing is less than or equal to 1. So this is the left hand side of Holder's inequality. This is the right hand side of Holder's inequality. We get this is less than or equal to 1. So this should be less than or equal to. Okay. So and because of this, this will be less than or equal to, and then so this comes to right hand side. So we obtain this inequality. That is the basic idea. Okay. So to obtain the Holder's inequality, we consider this function. We find its derivatives. Okay, but then we go for minimum. We obtain x of t is greater than x of 1. We obtain this inequality, and then in that, but we take suitable choice of a and b for t. We take t equal to a by b. So we obtain this inequality. This inequality in this with plus, if plus is not correct, it should be dot. So in that we consider for we go for aj and bj. We replace ab by aj and bj. We take proper choices for aj and bj. That helps us to obtain this inequality. Okay, so this is very important to prove certain norms, for certain norms on certain vector spaces. So here we stop. Thank you very much. If you have any doubts or comments, you may inform us through mail. Thank you.
మా గ్రూప్ లో పెట్టిన మొత్తం ఈ రోజు చేసుకుంటే మొత్తం ఇలా లైవ్ లీవ్ అన్నది అంటే మనం బ్యాక్ అంటే ఇక్కడ